If you recall, when we did a derivative of some composite function like this, we had to find the derivative of the outer function and then multiply by the derivative of the inner function. So just to remind you how the chain rule for derivatives works, in this particular example, if we write that as x squared plus 11 to the 1/2 power, recall that we found the derivative of the inside to the 1/2 power, whereby the derivative was 1/2 x squared plus 11 to the negative 1/2 power, and then we had to multiply by the derivative of the inside, where the derivative of the x squared plus 11 would be 2x. Now, if we're going to do integration, where we have a composite function, we have to realize that what we're doing is derivatives in reverse, where we have to have this proper derivative of the inside on the outside of the derivative. So, let's do a similar example of finding an integral going the other way. Suppose that it's x squared plus 11 to the 1/2 power x dx. We're attempting to do derivatives in reverse. And if we look at the inside, which is commonly referred to as u, we'll think of that as u, x squared plus 11. Remember that what this is supposed to be is a derivative, and we're going in reverse to find out what the original function was. So, like we had in the example of the derivative, we have to have this proper derivative of the inside function on the outside. And if we call this u, we have to have the proper du on the outside. The derivative of that inside would have been produced had you done the derivative going forward. So the derivative that u would have been 2x, and then theoretically we also have the differential dx, the indicator that we're doing the integral in x. But we don't quite have that. All we have here is just the x. But not really a problem. We can always do an adjustment. Let me go ahead and write that again. We have the integral of x squared plus 11 to the 1/2 power, and I'll put a little bit of space here because we want to have the derivative of the x squared plus 11 here on the outside. Well, we don't quite have it there, but we can put it there. We can put it there by simply making an adjustment. We would like there to be a 2x, so we simply multiply by the 2, provided that we compensate by multiplying by the reciprocal. So really you're multiplying by 2 over 2. We've compensated for the 2 by multiplying by 1/2. And now it's set up to actually do the integral, provided that we have the proper u inner function, which is x squared plus 11, and the derivative of that u, du, on the outside. And then going in reverse, we want to find what was the function that had now that for the derivative. Now note that you can always adjust by a constant, because multiple of the integral is just the multiple, the multiple of the integral. We can simply have a 2 and a 1/2. Do not do this if you have a variable. You cannot write a variable on the outside of the integral. That would be an invalid response. We could always do that with simply a constant. If you have to adjust by a variable, that would be a different type of of a substitution. So now we want to see where this came from. And you're thinking of it as the x squared plus 11 to the 1/2 power, and that was the derivative of the inside that would have been produced. So going in reverse, we end up having 1/2, and then we have x squared plus 11 raised the power by 1, 3/2, dividing by the new power, which is the same as 2/3. And if we simply simplify what we have up front, we have 1/3 of x squared plus 11 to the 3/2 power, and always remember to include plus c in order to be completely correct. And remember that whenever you do an integral, you're saying, if that were the derivative, what was the original function it came from? So you could actually attempt to find the derivative and see if you end up where you started.